Thank you, Murakami Sensei, for introduction. I'm Sato from Institute of Science Tokyo, formerly known as the Tokyo Institute of Technology. First of all, I would like to thank Dominique and other organizers for inviting me to this wonderful workshop. And also, I thank the financial support by the sponsors, including Murakami Sensei. Today, I will talk about chiral phonons in chiral and achiral materials. Let me introduce my main collaborators from Science Tokyo and Osaka Metropolitan University and Open University, Meiji University, Okayama University, University of Tokyo, and RIKEN. So today, Murakami Sensei and Chan Sensei and Toga Sensei and Kishine Sensei are also attending this workshop. This is the outline of my talk. First, I will discuss the angular momentum and chirality of phonons. Then I will discuss the chiral phonons in chiral materials such as alpha HGS and tellurium. This is not, I'm not familiar. Okay, and then I will discuss chiral phonon in achiral materials. Here, so the main player of this study is our former student Ishito, and also our former student Yuji Huang, and now Kusuno is our doctor course student. And here, so for the last part, please also visit our poster session. So let's discuss the angular momentum and chirality of phonons. The angular momentum of phonons was originally discussed by Russian researchers. They just said that the circularly polarized transverse phonons can carry angular momentum analogous to the spin of circularly polarized photons. It was published a long time ago. So then, Professor Li-Fa Chang and Professor Qian Liu recently also discussed the angular momentum of phonons in more detail, as so Professor Li-Fa Chang presented in the previous presentation. And the same author also predicted chiral phonon like this in two-dimensional materials such as monolayer tungsten selenide. This prediction was experimentally verified by Professor Hanyu Zhu using a pump and probe terahertz technique. Also, the angular momentum of phonon exhibit large phonon Zeeman effect. It is huge. And these pioneering works stimulate intensive studies on chiral phonons. But what is the definition of chirality? In the static case, it is clear. The chiral system is defined as the breaking of inversion and mirror symmetries. Okay, one typical example is right hand and left hand. Okay, it is clear. This definition still holds in the dynamical case. But how do we characterize the dynamical chirality? So in dynamic case, so Professor Baron said that chirality has two types, true chirality and false chirality. So here I will discuss the true chirality. So let's consider two enantiomeric states. It's not a static, it's dynamical states. Left hand state and right hand state. And true chirality means that left state can be converted to right state by spatial inversion, but not converted by the combination of time inversion and spatial rotation. This is a definition of true chirality. One example of such true chirality is like this. So this is an object propagating to one direction and also rotating. Okay, let's call L state. Then such L state can be converted to R state by the spatial inversion. So here, the sense of rotation doesn't change, but the propagating direction is reversed. Therefore, we can say that it is R state. However, the L state, by the time inversion, the L state becomes like this. And by operating the C2 rotation, its state go back to the L state again. So therefore, this satisfies the definition of true chirality. So the propagating and rotating object can be characterized by K dot L. K is momentum, and L is angular momentum. So the inner product of the polar vector and axial vector is pseudo vector. If it is non-zero, then we can say that it has true chirality. So such importance of the pseudoscalar is discussed in this journal. Author is Professor Kishine. So the importance is discussed. So please refer to this paper. And then, so today, Dominic presented the previous phonons, chiral phonon workshop. And actually, I attended 2 years ago the CCAM workshop, chiral phonons in quantum materials. That workshop was very, very useful for the participants. And in that workshop, we discussed how can we characterize chiral phonons. And during the presentation, I proposed that K dot L is a good measure of chirality. And I took a photo of the free discussion poster at the CCAM workshop. So here, they wrote what is important for the chiral phonon, such as chiral or circular or 1D, 2D, or 3D, or true or false, or pseudo-angular momentum, or what's the difference between pseudo-angular momentum and the angular momentum. This kind of thing are intensively discussed. So here, so they said that the characterization of the chiral phonon is a kind of Lugano test. They said Lugano test. So here it says Lugano test. I don't know who wrote it, but okay. Then based on this discussion, the organizer, including Dominic, organized the review paper or perspective paper, and it will be published in Nature Physics. And in that paper, in this paper, Dominic and other collaborators propose that the term axial phonon to encompass all phonons that carry angular momentum. So this means, chiral phonon should have not only the angular momentum, but also the propagating property. But if the phonon is just rotating, let's call axial phonon instead of chiral phonon. So this is a message of the paper. Yeah? Okay, so then the question is, are there truly chiral phonons? So what about chiral material? This is the first question. Actually, there are several theoretical investigations on chiral phonons in chiral materials. For example, Professor Kishine discussed the chirality of phonon in a chiral material, chromium ion sulfide. And Professor Murakami and co-workers also discussed the angular momentum in chiral material, Tellurium. And Dr. Hao Chen and collaborator discussed the angular momentum and also chirality in Tellurium. And there are several other important papers, such as the paper by Tsunetsugu and Kusunose, and also Kishine and co-workers, and this one. And these theoretical investigation stimulate corresponding experimental works. So here is the objective of our study. First is the observation of truly chiral phonons in chiral materials. The second is the investigation of the relationship between the circular polarization of light and the pseudo-angular momentum of phonons. For this objective, we performed circularly polarized Raman scattering spectroscopy on alpha HGS and tellurium. For this, we also calculate the first principle calculations of phonon dispersion and phonon angular momentum. So let's go to the next one. So alpha HGS has two enantiomeric structures because it is a chiral structure. One is left-handed HGS, and the other one is right-handed HGS. The space group is P3221 and P3121. The helical axis is along the C-axis. But here we focus on the right-hand HGS. So this slide shows the configuration of our circularly polarized Raman spectroscopy. For example, here, RL denote that right-handed circularly polarized light is incident and left-hand circularly polarized light is scattered. And according to the momentum conservation law, like this, so the incident light and the scattered light are propagating in the opposite direction. So the excited wave number of phonon is about 1/80 of the momentum of A point. So it is quite small, but still not negligible. Not negligible. It is important. Okay, now I show you the result, experimental result. For the right-handed HGS taken at room temperature. The left-hand side is anti-Stokes and right-hand side is Stokes spectra. And according to group theory, the Raman active mode include 2 gamma-1 singlets and 5 gamma-3 doublets. And in our measurement, we identify 2 gamma-1 and 4 gamma-3 mode. And here we focus on the 4 gamma-3 mode here. Let's magnify. So this is a magnification. The left-hand side shows the anti-Stokes spectra for the 4 gamma-3 mode, and right side is the Stokes spectra for the 4 gamma-3 mode. So as you can see, the gamma-3 mode clearly split into 2 components depending on RL and LR polarization configurations. And what is important here is, for example, gamma-3 2 mode, the LR configuration has higher Raman shift, but the next one, RL configuration has higher energy. So depending on the mode, the direction is opposite. So to understand the direction of the splitting, I asked Ishito-san to calculate the first principle calculation to see the angular momentum of phonon. So at that time, I thought that it may be related to the angular momentum. So this is a result of the phonon dispersion. So as you can see, at each gamma-3 mode, the energy is split linearly along from gamma point to A point. And so here, so you can clearly see the linear splitting. This is the reason of the splitting observed in the Raman spectrum. However, when we calculate the angular momentum, the sign of the angular momentum does not correspond to the direction of the splitting in the Raman spectrum. So then I discussed with Murakami sensei. At that time, he was in the same department at Tokyo Institute of Technology. So we can easily discuss with Murakami sensei and Tian Chan-san. And they proposed that instead of angular momentum, we should calculate pseudo-angular momentum. So yeah, luckily, they are writing a paper here independent of us about the new definition of the pseudo-angular momentum. So this is the definition they propose. And based on this definition, we calculate the pseudo-angular momentum of phonon in alpha HGS. So this is the result. So the black one means the pseudo-angular momentum is 0. And the blue and red one means the pseudo-angular momentum is -1 and +1 respectively. And what is important here is the splitted gamma-3 mode always has +1 or -1 pseudo-angular momentum. Okay, let's compare with experiment. So this is a Raman spectrum, but now we rotate the Raman spectrum by 90 degrees. So the horizontal axis is Raman intensity, and the vertical axis is Raman shift. And compare the pseudo-angular momentum. Now we can see the clear correspondence between the direction of the splitting in the Raman spectrum and the sign of the pseudo-angular momentum. For example, RL corresponds to the -1 pseudo-angular momentum, and LR corresponds to the +1 pseudo-angular momentum. Therefore, we can say that we can verify the conservation of the angular momentum during the Raman process experimentally with the help of the first principle calculation. Okay, so then we move to the case of tellurium. This is a very similar. So tellurium also has the two enantiomeric structure, left tellurium and right tellurium. But unfortunately, we did not identify the handedness of tellurium because sometimes it was hard, and we have to destroy the sample, and it was not so easy. But let's try the Raman spectrum measurement. So this is the result. Similar to the case of alpha HGS, we observe the splitting in the gamma-3 mode. And then compare with the phonon dispersion curve. So this is the result for the right-handed tellurium. By the way, this result is fully consistent with the result given by Dr. Hao Chen. Yeah. And if we compare our experiment, the corresponding is very, very good. So this means that actually our tellurium sample is right-handed tellurium. So our technique can identify the handedness of chiral crystal by optical means with help of first principle calculation. So we don't have to destroy the sample. This is a very good advantage of this technique. Okay, so, okay, already 20 minutes past. Yeah, okay, so I have to, okay, so, Dr. Tian Chan also investigates the chiral phonon in tellurium in her paper, and yeah, the experimental result is similar to us, but she also discussed the connection between the chirality of phonon and the topological nature. So, for example, here the PAM is connected to the Chan number of phonon. Also, I want to mention a very interesting result presented by Dr. Ueda. So, alpha quartz is a very typical helical and chiral material, one of the most popular one. And he used this material and measure resonant inelastic X-ray scattering. And this is a result of RIX and with circularly polarized X-ray. The signal is like this. And the advantage of this technique compared to the Raman technique, the wave number of X-ray is much, much larger than compared to the optics or visible light. So as you can see here, the horizontal axis is, so two or three orders of magnitudes higher than the optics. So they can clearly see the signal depending on the handedness of the left and right-handed quartz. Although I have to say that the spectral resolution of this technique is not very good enough to distinguish each phonon mode, but it is a clear evidence that they observe the chiral phonon. Another important result is connected to the thermal sheath. So here, Professor Togawa demonstrates that. So he also used alpha quartz, and he applied the thermal gradient. So here they put the heater here and heat the quartz. Then they measure the spin signal using the inverse spin Hall effect here, and this is the result. So the spin Hall signal, inverse spin Hall signal, increase as a function of the temperature gradient, and also the sign of the signal is reversed by reversing the helicity of the crystal. So therefore, it is a clear evidence that the chiral phonon carries angular momentum, and then it is converted to the spin signal. Okay, so let's go to the next one. Now we know that chiral phonon exists in chiral material. Now another question is, do chiral phonons only exist in chiral material or not? So to see this, we calculate the true chirality. It is characterized by K dot L. Now we use as an example gallium arsenide because it is achiral but non-centrosymmetric material. And our former student, Yuji Huang, calculates the phonon dispersion band structure and also K dot L. So as you clearly see that K dot L is non-zero around the W point. Therefore, we can say that chiral phonons are ubiquitous in non-centrosymmetric crystal. It is not limited to chiral materials. It is my message. Now, the second question. Okay, now we can say that the chiral phonons exist in non-centrosymmetric materials. Now, is it possible to excite chiral phonons in centrosymmetric materials? To verify this, we chose ferroaxial material, nickel titanate. It has illuminate structure, but it is centrosymmetric. It is an insulator and paramagnetic at room temperature. And at a certain temperature, Tc, and below this, it shows ferroaxial phase. And ferroaxial phase means there are two kinds of domain structure. Oh, sorry. Okay, so A plus and A minus, depending on the direction of the electric dipole moment. And this material is good because this does not exhibit ferroelectricity and ferromagnetism. Therefore, any phenomenon purely originating from ferroaxiality. Now I can show you the result. Okay, I have to hurry a bit. So this is a circularly polarized Raman spectrum of this material. And okay, so this graph is important. So now we use a front side of this material. We can see several EG mode. EG mode means doubly degenerate mode. Now when we flip the sample like this, then, sorry, no, before we flip the sample, we change the configuration from RL to LR. You can clearly see that the intensity significantly difference between RL and LR. This is called Raman optical activity, but it is very huge. Now we can characterize the magnitude of Raman optical activity using this equation. And at this Raman shift, rho reaches 0.5. This is huge. Okay, so now question is this related to ferroaxial order or not? To verify this, we flip the sample, because by flipping the sample, ferroaxial order changes the sign. Okay, so this is the result. The upper panel is a result for the front side. The lower panel shows the result for the back side. You can see that the sign is reversed between these two. So this result clearly verifies that this change comes from the ferroaxial order. Okay, and so conventionally, the Raman optical activity has been known for two cases. One is natural ROA, and the other one is magnetic ROA. And natural ROA was observed in chiral material, but the signal was very small. The rho was the order of 10 to the minus 3. This is because this mechanism comes from the contribution of electric dipole and magnetic dipole, or electric dipole and electric quadrupole terms. So therefore, it is a higher order effect. However, our rho is about 0.5. So to understand this, we check the excitation wavelength dependence. So here, previously, we used 785 nanometer. Okay, I have to skip. Yeah. Now we change the wavelengths, and you can see now by changing the wavelengths, the Raman optical activity is drastically reduced. So this means that the contribution of the electric dipole is dominant. So for symmetry analysis, please refer to this paper. Okay, so by using this technique, we can make an image of a ferroaxial pattern like this. I want to stress that we don't have to apply the electric field. So this is a clear advantage of this technique. So finally, I want to discuss the chiral phonon nature of this phonon. Because it has central symmetric symmetry, so as an eigenmode, it shouldn't have the chiral nature. But during the Raman process, we can selectively and detect and selectively excite mode. So in that sense, the two degenerate mode can be separated into so E2 and E1 mode, and each mode has angular momentum, and we can see that we can excite the three chiral phonons. Okay, so I have to skip the summary. Thank you for your attention.
Thank you very much.